Good morning, Chance. Today we study a classic vortex model called the Rankine Vortex. This example is useful because it connects three important ideas in fluid mechanics: vorticity, circulation, and vorticity flux. It also shows how Stokes' theorem appears naturally in a rotating flow. We consider a steady axisymmetric flow in cylindrical coordinates r, theta, and z. The velocity field is purely tangential. This means there is no radial velocity and no axial velocity. The velocity vector is therefore u equals 0 in the radial direction, u theta of r in the tangential direction, and 0 in the z direction. The tangential velocity is defined piecewise. Inside a circular core of radius a, the velocity is u theta equals omega times r. Outside the core, the velocity is u theta equals omega times a squared divided by r. This flow is called a Rankine vortex. Inside the core, the fluid rotates like a solid body. Outside the core, the flow behaves like a free vortex. Our goal is to determine the vorticity, the circulation around a circle of radius r, and the vorticity flux through the disk enclosed by that circle. First, we compute the vorticity. The vorticity is defined as the curl of the velocity field. For axisymmetric swirl flow with only a tangential velocity component that depends on r, the vorticity has only a z component. It can be written as omega z equals 1 over r times the derivative with respect to r of r times u theta. We first compute this inside the vortex core. Inside the core, the tangential velocity is omega times r. Multiply by r and we obtain r times u theta equals omega r squared. Dividing by r gives omega z equals 2 omega. Therefore, the vorticity vector inside the core is 0, 0, 2 omega. Next, we compute the vorticity outside the core. Outside the core, the tangential velocity is omega times a squared divided by r. Multiplying by r gives omega a squared. This is constant. The derivative with respect to r is therefore 0. This means the vorticity outside the core is 0. So the outer region is an irrotational flow. Now we compute the circulation around a circular contour of radius r. Circulation is defined as the closed line integral of the velocity dotted with the line element. Along a circle of radius r, the velocity is purely tangential and constant along the contour. The line element along the circle is r d theta in the theta direction. The dot product of velocity and the line element becomes u theta of r times r d theta. Therefore, the circulation equals the integral from 0 to 2 pi of u theta of r times r d theta. We first consider the case where r is smaller than the core radius a. In this case, the tangential velocity at radius r is omega times r. Substituting into the integral gives gamma of r equals the integral from 0 to 2 pi of omega r squared d theta. Performing the integration gives gamma equals 2 pi omega r squared. Next, we consider the case where r is larger than the core radius. In this case, the tangential velocity at radius r is omega times a squared divided by r. Substituting into the circulation integral gives gamma equals the integral from 0 to 2 pi of omega a squared d theta. This gives gamma equals 2 pi omega a squared. Notice that outside the core, the circulation is constant and does not depend on R. Finally, we compute the vorticity flux through the disk enclosed by the circle. The flux is defined as the surface integral of the vorticity dotted with the surface normal. The disk lies in the xy plane, so the normal vector points in the positive z direction. The area element in cylindrical coordinates is r dr d theta. If the radius r is smaller than a, the entire disk lies inside the vortex core. The vorticity is 2 omega everywhere. Integrating 2 omega over the disk gives 2 pi omega r squared. If the radius r is larger than a, only the core contributes to the vorticity flux, because outside the core, the vorticity is 0. Therefore, the integration is performed only from r equals 0 to r equals a. This gives 2 pi omega a squared. Comparing the results, we see that the circulation around the contour is always equal to the vorticity flux through the enclosed area. This confirms Stokes' theorem. The circulation around a closed curve equals the flux of vorticity through the surface bounded by that curve. The key physical insight is that the vorticity is confined to the vortex core. Outside the core, the flow still circulates, but the local vorticity is 0. Once the contour encloses the entire core, increasing the radius does not increase the circulation anymore.